Morning all. So in today's lecture, let us discuss about spherical aberration. Okay. So now let us take a convex lens of large aperture. Okay. Now I placed a point source O. This is point source O on principal axis of this convex lens. Okay, principal axis of this convex lens. Right? Now, the rays which are incident nearer to the axis, we call them as paraxial rays. We call them as paraxial rays. Okay. The rays which are incident at a rim of the lens, these rays which are incident at a rim of the rays, we call them as marginal rays. We call them as marginal rays. Okay. Now this paraxial rays will form their image or will come to focus on principal axis at some point IP, and these marginal rays will come to focus on principal axis at some point IM. Okay, and the intermediate rays which are present will come to focus between IP and IM. So in such a way, paraxial rays form their image at IP, marginal rays form their image at IM. So now from this it is clear that paraxial rays form an image at a distance than the marginal rays from the lens. So image is not sharp at any point on the axis. So this failure or inability of the lens, this failure or inability of lens to form point image for point size object, we call it as spherical aberration. So what is the spherical aberration? The failure or inability of the lens to form a point image of an actual point object is called as spherical aberration. So when we used a point source, image must also be a point image. But instead of point image, here we are getting different images at different distances. Paraxial rays has formed the image at IP, marginal at IM, and the intermediate rays form the image in between IP and IM. Means the image is not sharp at any point. We are not getting the point image for point size object. So only we call it as spherical aberration. Then why this spherical aberration forms? Let us see that. So why spherical aberration forms means, the reason comes out to be, here the lens is supposed to be divided into circular zones. Means lens is divided into circular zones, and here the focal length slightly vary with radius of zone. Okay, that is, we can say that different zones are having different focal lengths. Different zones are having different focal lengths. So, the focal length of marginal zone, marginal means, now if this is the lens, we are saying it is divided into different circular zones. So, the zones near the rim of the lens we call marginal zones, right? So, the focal length of marginal zone will be lesser than focal length of paraxial zone. So, paraxial zone is the zones which are nearer to the axis. The zones, circular zones nearer to the axis we call paraxial zones. So, focal length of, mathematically it is proved that the focal length changes with radius of zone. So, the focal length of marginal zone will be less than the focal length of paraxial zone. So, only here marginal rays form in front of the lens compared to that of the paraxial rays. So, here paraxial rays, as they have greater focal length, they form their image at a distance from the lens, center of lens, compared to that of marginal rays. Okay. In other words also we can say that, as marginal rays are incident at a rim of lens, they suffer greater deviation. They suffer greater deviation than paraxial rays. Okay. So, only they form in front of the lens compared to that of the paraxial rays. Okay. Now, next, the distance between this IM and IP, we call it as longitudinal spherical aberration. So, what is longitudinal spherical aberration? The distance between IM and IP, the image formed by the paraxial rays and image formed by the marginal rays, we call it as longitudinal or axial spherical aberration, right? Now, let us take a screen. First, you place the screen at IM. Screen is AB. So, what we will observe on the screen means, we will get a circular disc in such a way, and this circular disc is sharply focused at the center. Okay, sharply focused at the center by marginal rays and diffused as we go towards the outer edges. Similarly, now remove from IM and place the screen at IP. At that position also we will find that at the center of this circular disc, means on the screen the image is formed in form of a circular disc. At the center of circular disc, it is sharply focused. The disc will be sharply focused due to the paraxial rays and diffused as we go towards the outer edges of the disc. Now, just move this screen between this IM and IP. At one particular point, you say here, okay, at some PQ. At one particular point PQ, we will see that the size of disc reduces, means it becomes minimum. the size of a disc becomes minimum. The size reduces at PQ. Okay. So only now at this position, this circular disc, due to its smallest cross section, we call it as circle of least confusion. We call it as circle of least confusion. Okay, due to its smallest cross section, we call it as circle of least confusion. Right? Now here you just observe carefully. At PQ position, now see, this is marginal ray, this is paraxial. Now this is here also, this is marginal ray, this is paraxial. Means at this PQ ray, the marginal and paraxial rays are combining, okay, or intersecting with each other. The marginal and paraxial rays cross each other also, we can say. At that particular point, the size of the disc, circular disc, is reduced, and this we call it as circle of least confusion. And this circle of least confusion can be taken as a nearest approach to the point image. Nearest approach to point image. Okay. So now we can say that at point PQ we obtain a best possible image of uniform sharpness. So in other two cases, what happened? At center it is sharply focused. As we go at outer edges, it is diffused, we said. But here this circle of least confusion will be of a uniform sharpness. Now the radius of the circle of least confusion, we call it as lateral spherical aberration. The radius of circle of least confusion, we call it as a lateral spherical aberration. So this is about spherical aberration. Why spherical aberration is formed? Because here the failure or inability of the lens to form point size image for point size object, we call it as spherical aberration. Here the lens is supposed to consist or divided into some circular zones, and the focal length of every zone changes with the radius. So only what happens? The focal length of marginal zone will be lesser than paraxial zones. So only the marginal zones will form their image or focus in front of the lens first, and then after the paraxial rays will focus at a distance from that of the lens. So only we are getting this spherical aberration. So what is longitudinal spherical aberration? It is nothing but the distance between IM and IP. What is lateral spherical aberration? It is nothing but the radius of circle of least confusion. Thank you for watching. If you like my video, subscribe it. Thank you.